Dear viewers, greetings to all of you. In this video, we are going to discuss intersection of open sets in the metric space. As usual, before proceeding for the main result, we shall discuss some preliminaries. Please recall concentric spheres in Euclidean geometry. On your screen, we are showing a sphere with center at x and having some certain radius. Now, if we reduce the radius and keep the center as x, then what happens? You see, now you have another sphere with the same center x but having a lesser radius. So you can very easily see that the sphere with smaller radius becomes a subset of the sphere with bigger radius. So this is very obvious in the natural thinking or the natural geometry, which we generally call as Euclidean geometry. But our curiosity is whether this property is true in the general setup of a metric space. Let us see what happens in a metric space. So the situation of concentric spheres in metric space is to be discussed, and as you know, in the setup of metric space, an open sphere doesn't necessarily look like a sphere or a ball in the general sense. It may have a different shape, and in many times, in abstract metric spaces particularly, you won't be able to visualize the open spheres. But to just have a motivation, let us see the open sphere in RD, one-dimensional space, and with the standard metric, you have the real line now with center as 0, and the metric is the standard metric. Now, if we imagine for an open sphere with radius 1 and center at 0, the open sphere will be written as S10, and that S10 is nothing but an open interval with ends point -1 and 1. So it is in fact an open interval, and if we increase the radius of this sphere, suppose 1 is increased to 2, then the open sphere, which is S20 now, is again an open interval with endpoints -2 and 2. So here you can see that if we increase the radius of the open sphere, then the bigger sphere overlaps the other sphere if we are keeping the center as the same. So in the setup of RD, we can see that the sphere with the smaller radius is a subset of the sphere of the bigger radius if both the spheres are concentric. Now let us move and see whether it is true in general setup. So in the general setup, we have taken a metric space XD, and now we are defining an open sphere in metric space like SRX is equal to the set containing all those points y in X such that dxy is less than R. This we already know, and with this definition, what we want to prove is that if R1 is less than or equal to R2, it implies that the sphere with the radius R1, which is SR1X, is a subset of SR2X. So this is we want to prove. Now in order to prove it, let us take a point y in SR1X. Now if y is in SR1X, it implies that dxy is less than R1. But since R1 is less than or equal to R2, we have dxy less than R2 as well. But when dxy is less than R2, it means that y is a member of the sphere SR2X. And therefore, we have taken a point y in SR1X, and we have proved that y belongs to SR2X, and it proves that SR1X is a subset of SR2X. So if we are considering two concentric spheres, then we can very easily see that the sphere with the smaller radius is a subset of the sphere with a bigger radius. Now let us extend this result for finite number of spheres. Suppose we have spheres now SR1x, SR2x, SR3x and SRnx, and we want to choose the sphere which is a subset of all these spheres. So what we have to do? Simply take the minimum of all these radius. So take the minimum of R1, R2, R3 and Rn, call it R. Then obviously you will find that the sphere SRx becomes a subset of SR1x, it becomes a subset of SR2x, it becomes a subset of SR3x, and similarly if you proceed on, SRx becomes a subset of SRnx. In symbols, we can write that SRx is a subset of SR alpha x, where alpha varies from 1 to n. So this is the situation of concentric spheres in metric space. Now we will use this information in discussing the intersection of open sets, and for that we firstly discuss the intersection of two open sets. So here we have taken an open set G1, and just for understanding we have considered a rectangle to represent this open set. We are also recalling the definition of an open set, and we say that a set G is open if for arbitrary point x in G we have an open sphere SRx subset of G. It means you have taken a set G, and if you take any point in G and you find an open sphere centered at that point like SRx, and that SRx, that open sphere becomes a subset of the set, then the set becomes an open set. So here G1 is an open set, and we take a point X which is an arbitrary point in G1. Then by the definition we will have an open sphere SR1X which will be a subset of G1. Now suppose that this X also belongs to another open set G2. Now thinking in this way that now X is an element of G2 which is an open set, we will again have an open sphere SR2X which will be contained in G2. Now let us look at the intersection of G1 and G2. So this is the intersection part of G1 and G2, and you still see that the open sphere SR2X is subset of G1 intersection G2. So what we find that X is an arbitrary point in G1 intersection G2. This we can always consider it like to be, and SR2X is a subset of G1 intersection G2. So X is an arbitrary point in G1 intersection G2, and we have an open sphere centered at X which is a subset of G1 intersection G2, and therefore by the definition of open set which we have just recalled, it gives us that G1 intersection G2 is an open set. Now we have two observations. What are those? Let us see. The first is, you can see that between SR1X and SR2X, the radius of SR2X is smaller and it becomes a subset of the intersection. So we find that a sphere with the smaller radius becomes a subset of the intersection. This is a general observation regarding that, and this idea can be extended to finite number of open sets, because if you take another set G3, again you will have three open spheres. Take the open sphere with the smallest radius, and that open sphere will become a subset of the intersection, and so on. So let us see whether this idea can be extended to finite number of open sets. So in a metric space, we are going to prove that the intersection of finitely many open sets is an open set. Let us proceed for the proof. Now in the proof, we have taken ED as a metric space, and we have taken G1, G2, Gn as a family of open sets in E. So certainly they are finite in numbers. And what we do that we take G as the intersection of all these open sets. So G becomes equal to G1 intersection G2 intersection so on intersection Gn, and in symbols we can write that G is equal to intersection alpha running from 1 to n G alpha, and we want to prove that G is an open set. So in fact, we want to prove that this intersection is an open set. Now, if this intersection is empty, then it is an open set, that we know by the definition of open set. If the intersection is not empty, then we take a point X in G, which is arbitrary point. Now, if X belongs to G, then what will happen means that X belongs to G alpha for each alpha equal to 1 to n. It means X belongs to G1, X belongs to G2, X belongs to Gn as well. But if X belongs to G1, it means you have an open sphere SR1X. If X belongs to G2, you have an open sphere SR2X, which is a subset of G2. If X belongs to Gn and Gn is an open set, therefore you have an open sphere SRnX, which is a subset of Gn. So we can write that for each G alpha, we have open spheres SR alpha such that SR alpha is a subset of G alpha. This is because each G alpha is open. So what we find that we have taken an arbitrary point X in G, and since G is the intersection of all these open sets, X belongs to each of these open sets, and since these are open sets, for each of these open sets we have open spheres such that each open spheres are subset of the corresponding open set. It means SR1 is a subset of G1, SR2 is a subset of G2. We have escaped writing X because the spheres are concentric, and we can just ignore to mention X here. So SR1 is a subset of G1, SR2 is a subset of G2, and so on. Now, what we do that we take the minimum of these radius R1, R2, Rn, and we call it as R. Therefore, R is greater than 0, and now SRx becomes a subset of all SR alpha, which are subset of G alpha. And so SRx becomes subset of the intersection from alpha to n G alpha, which is nothing but G. So we have taken an arbitrary point X in G, and we have found that we have an open sphere SRx, which is a subset of G. It gives that G is an open set, which is nothing but the intersection of finite number of open sets G1, G2, Gn. And therefore we prove that intersection of finitely many open sets is an open set. Now let us check whether this property is going to hold when the family contains infinitely many open sets. The answer is no. Let us see how. Now we have taken the usual metric space Rd, and we are considering Gn as the open intervals with endpoints -1 by n and 1 by n. So if n runs from 1 to infinity, we have infinitely many Gn here. And if we take the intersection of all those Gn, then since 1 by n and -1 by n both tend to 0 when n tends to infinity, this intersection is nothing but the singleton containing 0. But in metric space Rd, which is the usual metric space, we know that singletons are not open. So the singleton 0 is not open. So we have taken infinitely many open sets, because you know open intervals are open sets in Rd. So we have taken infinitely many open sets in Rd, and we have found that intersection of those infinitely many open sets is not an open set. So the property which we have studied regarding intersection of open sets is true only for finitely many open sets. If you take intersection of infinitely many open sets, it may fail to be an open set. So with this, we are closing this video. We have discussed union of open sets in another video. We have discussed intersection of open sets in this video. In the next video, we will be talking about union and intersection of closed sets. Till then, bye. Thank you very much.